This is the first problem for some open-ended synthesis using alpha carbon chemistry. As usual, we want to take a look at this structure and see if there's any bonds that looks like we know how to make. And of course, there's an aromatic ring here. We know how to make this bond here. We know how to make this bond. Perhaps we can use that to make a reagent that might allow us to add this piece, maybe. These three groups off of this cyclopentane ring don't look to be all that interesting, to be honest. So we don't know where to start. But if we look at the alkene could have come from the dehydration of an alcohol, maybe. And so if we had an alcohol here or here, that would allow us to make the alkene and get to the final product. And of course, an alcohol could have come from a carbonyl that got reacted with a Grignard. And once we get to a carbonyl, then we have some alpha carbons that we can deal with, and we can do some chemistry from this chapter. Now, of course, we don't have to solve this using alpha carbon chemistry, but my goal is to do that as I want to exhibit some of that, those synthetic tools. So let's redraw this molecule, because I want to keep it up here as a target, but I'm going to redraw it and look at the potential to have an alcohol at one of those positions on the 5-membered ring. And let's try the right side first. And I'm just going to abbreviate the phenyl for now. We'll get back to that. And so, of course, I could, assuming I don't react with the carbonyl on the phenyl, I could eliminate this to potentially make this alkene. But I think now that I look at it, I could also eliminate it to go down to make the alkene on the vertical bond. And of course, I don't want to have that that possibility. I want to make this alkene as much as possible. So maybe I want a carbonyl right here that could allow me then to eliminate and get the most substituted alkene. So let's erase this and put the carbonyl right here. I hope I've convinced you at this point that an alcohol is really a central functional group when we think about synthesis. So this alcohol could have been a carbonyl right there. And so let's keep exploring this and see if I can get this to work. And I shouldn't ignore the phenyl anymore because there is a group on there that I probably want to maybe protect. So in fact, I'm going to protect that just to make sure that anything that happens to that carbonyl up here does not also happen to the carbonyl here. And of course, if I added a Wittig, a Wittig would work to add the 3 carbons, but it wouldn't help me get to this alkene. But if I added a Grignard and then eliminated, I could get to that alkene. So that seems pretty reasonable. Now I have a carbonyl. I've got an alpha carbon. I've got a beta carbon. And we learned how to add groups to the alpha carbon. Typically, the alpha carbon is nucleophilic. If we add an electrophile to the alpha carbon, like a 3-carbon alkyl bromide, that would totally work in this case. Typically, the beta carbon, if we have some unsaturation here, is electrophilic. And so if we add a nucleophile, which would be shaped like this piece, nucleophilic at this position, probably with a cuprate, we could add that piece to our carbonyl compound. And we can actually add beta and then alpha in the same step, if you remember that. So let's explore that a little further. So now if I had this alpha-beta unsaturated carbonyl, I could also, and I'm actually going to draw the proper sequence here. The first step would be using the cuprate that looks like this. And again, I'm going to keep my carbonyl protected on my my aromatic ring substituent because I don't want that to react in any way here. So if I take cuprate and something that looks like this, and so the cuprate, let me just move the copper a little closer here. So the copper would be attached at the benzylic position. And of course, we need another ligand on the copper. Remember that the coppers typically have 2 R groups and a lithium. So I'm going to use CN here as my other R group because it doesn't transfer. It's a non-transferable ligand. And so I don't have to I don't have to make twice as much of this as I need in order to transfer it to the beta position. I can just make one equivalent, make my copper, and then I need some lithium here. We'll put that right here. So that could be step 1. Step 2 then, without acid workup, I would end up with an anion at the alpha position, and I could just add propyl bromide and alkylate it straight away. So now my target becomes certainly making propyl bromide, but making the ligand for my cuprate and making this alpha-beta unsaturated cyclopentenone. And again, let's remember the rules. We can start with benzene. We can start with alcohols of 1 to 5 Cs. Now this is artificially limiting. In real life, this wouldn't be that limiting, but since this is an exercise to help us learn the material and show that we can take these concepts and put them together in a 12 or 10-step synthetic pathway, we're going to have some artificial constraints just to make sure that we are using as much of our learned techniques and concepts as possible. So we can start with benzene and alcohols of 1 to 5 carbons. So those would be the rules for all 3 of these problems. Let's then keep working and go backwards to make our cyclopentenone, and we can actually do that with a 5-carbon chain that looks like that, right? Because this is an aldol product. If we envision making that double bond right there, we can make a double bond between the 2 end carbons here. The aldehyde's more likely to be attacked by the nucleophile than is the ketone, and that would leave us with this cyclopentenone. The only question now is, how do I make this from monoalcohols of 1 to 5 carbons? That is the question. So let's think about this. If I had, there's a couple ways we could make this. One way is probably using acetylene and an epoxide to ring and open the epoxide and end up with 2 functional groups on either end of our functional chain. I think I'm going to try that here because I know how to turn an acetylene into a methyl ketone, and certainly I can turn a primary alcohol into an aldehyde. So let's give that a shot. Can I make this from, say, this compound? And actually I think it's going to have to be protected, so let's go ahead and do that. Actually, no, I don't want to protect that. What I want to do is I want to use this alkyne. So then I can expose the ketone, oxidize the aldehyde or the alcohol to the aldehyde, and I'll have my desired product or desired intermediate. How do I make this? Well, this has 3 carbons attached to the alkyne. I can only add 2 via an epoxide ring opening, so I think I have to do 2 different sequences here. So I can get to this alkyne by using this primary alcohol and adding 1 carbon via formaldehyde, and I can get to this intermediate from these 2 compounds, acetylene and the epoxide. I can get to the epoxide and acetylene actually from the alkene. The alkene can be epoxidized to make the epoxide, and the alkene can be have 2 bromines added to it, and then do a double elimination to get to the acetylene. So how do we get to the alkene? I can get to that by eliminating ethanol. So here I can make my 5-carbon species. It is a roundabout way, and of course the reality is we can probably buy this from Aldrich Chemical Company. So in real life we wouldn't try to make this, but again it's just good for us to practice our synthetic skills this way. So I've made this piece now. I need to make my cuprate. So how do I do that? Well, we know that a cuprate comes from copper chloride and 2 lithium species, but I want to put a cyanide in there, so I'm going to use copper cyanide in 1 lithium species. That lithium species will have to look like this. And I can make that lithium species from the bromine, so I know how to make a benzyl bromide. And you'll see my ketone remains protected, because if I turn this into a benzyl lithium, it will attack any ketones that are present. So I'm going to keep this protected while I make my benzyl bromide. I know how to make the benzyl bromide from the NBS oxidation of the benzylic position. And I can add this methyl. Actually, I can't add the methyl when they're to acetophenone, but I could add a bromine to acetophenone and ultimately get to, yeah. So this is what I was thinking, and I'm going to erase this. I was thinking of methylating acetophenone via Friedel-Crafts alkylation to put the methyl here. And of course, this is a meta-director, so that would work in terms of the regiochemistry. However, this is a deactivated ring, so Friedel-Crafts alkylation won't work here. But I could brominate here. That's no problem. I could get a bromine here, then I could protect my ketone. And the bromine in this position could eventually become a Grignard, and I could add formaldehyde to it to add 1 carbon to my chain. So I think I'm going to do that. I'm going to brominate, and then that would give me, if I added formaldehyde, that would give me an OH right here, which a couple steps I could turn into the lithium. So that's not really a problem. And then of course we can get to acetophenone from benzene and acetyl chloride, and I can get to acetyl chloride from ethanol. So I'm not going to show that in blue, I'll show that in green when I go back through the synthetic pathway. So let's go forward now. Let's go forward. I'm going to start with ethanol down here. How do I do that? Br2 to add 2 bromines. Then I need to, no, I'm sorry. This is not what I want to do right here. I want to eliminate, probably using, I could use sulfuric acid and heat. But I prefer to use tosyl chloride, I think. And then let's use DBU, non-nucleophilic base. We can eliminate. And then now I can use my first step is bromine addition. Second step would be excess NaNH2 to affect the double elimination to produce both pi bonds for the alkene. And then of course, if I want the epoxide, I can just use MCPBA or really any other peroxy acid. MCPBA I think is easiest to use and easiest to purchase. Now I have these 2 reagents. I'm going to, first step is to NaNH2 deprotonate the alkyne. Second step is to add the epoxide. And the third step is to work that up. I'm going to use NH4Cl, ammonium chloride, just as a source of, mild source of protons. And that will get me to this 4-carbon species. And then I can take it to the 5-carbon species by, first step would be converting the OH into a bromine, PBr3. Second step would be converting my bromine into a Grignard. Third step would be adding formaldehyde to the Grignard. Fourth step would be NH4Cl, ammonium chloride. So we're extending the chain by 1. Now I have this 5-carbon species. I think what I want to do here is to create the ketone first. So mercury sulfate, sulfuric acid, and water will create the ketone. Second step is PCC oxidation to the aldehyde, and that won't affect the ketone, so I'll have this species here, the ketoaldehyde. And then I can do a aldol reaction to get to my 5-membered ring. This will be a cyclization, loss of water, formation of the alpha-beta unsaturated piece, and I'm going to erase this line if I can. That's just a little bit interfering with what I want to look at here. So now I have my alpha-beta unsaturated compound. I need to make my lithium cuprate, and I need to make my alkyl bromide. So let's go back and look at the lithium cuprate. I'm going to use a different color for that. I can make acetyl chloride from ethanol, 1 via Jones reagent, oxidize the heck out of it to make acetic acid, and 2-SOCl2 pyridine to make acetyl chloride. And then I can, of course, mix those two together in the presence of aluminum trichloride, and I could make acetophenone. And then I can brominate acetophenone. I'm going to move my arrows up so I have a little more room to write. I can brominate acetophenone by bromine and iron tribromide. And my second step would be protection of the ketone via H2SO4 and ethylene glycol to make the acetal. Then I can convert my bromide into the benzylic alcohol via converting it into Grignard. Second step would be reacting it with a 1-carbon aldehyde, formaldehyde. And the third step would be ammonium chloride. And then I have my alcohol. And then I can convert the alcohol into a bromine and into a alkyl lithium. First step would be PBr3. Second step would be essentially 2 equivalents of lithium. Remember that lithium only has 1 electron to give up, and so I need to create a bromide and I need to create a carbon anion. And to do that I need 2 additional electrons, so I need 2 lithiums. And the byproduct here will be lithium bromide. So I have my organolithium now. I can mix that with copper chloride, and that will take me right to here. To make the alkyl bromide, of course, that's pretty simple. PBr3 will react with propanol. And so now I'm almost done, actually, I think. You can follow the green arrows now. I'm going to mix. The first step is adding my cuprate reagent to the beta position. The second step is alkylating the alpha position, and then I get right to here. And then it looks like we want to add a Grignard to this, and that's going to be magnesium bromide here. And then the workup will be, I betcha we could do all of this. Let's work this up with H2SO4, strong sulfuric acid. That will help us eliminate the alcohol and deprotect the ketone, and all at once. So I think that is what we're looking to do here. And so I need to make my Grignard. Well, of course, this comes from the propyl bromide, and I just made that right here from propanol, so I don't think I need to show you how to add magnesium to this to make the magnesium or the propyl Grignard. But that would be how I would produce this compound. So the in fact, my strong acid workup would take me right to the desired product. It wouldn't actually take me to this intermediate here. I'll circle this intermediate in red. We're not really going to stop here, because if I work it up with strong acid, I can protonate the alkoxide that's formed during the Grignard and making the OH. Strong acid then is used to eliminate in the most thermodynamic fashion, so that would give me this alkene. And strong acid is used to remove my ethylene glycol and convert it back to the ketone. So I think we could do all of this here. We may need a couple extra steps, but really it should all work just with the strong acid step. So this would be my many-step sequence to make this compound. All right, here's problem 2 for this video. And we have an apparent ketone. We don't have to search for the ketone like we did last time. We've got our ketone, we've got some alpha substituents, we've got a beta substituent. So this might proceed very similarly to what we just saw, where we make the we produce a cuprate to add to the beta position. We produce an alkylating agent to add to the alpha position. So let's work backwards here and see what we might need. I think if we have this compound and we react that with the isopropyl cuprate, and we can use 2 isopropyls on here because that's pretty cheap. So isopropyl CuLi, and that would be the first step. Second step would be this fancy aromatic compound. Let me try to draw that a little better. And if I had a, this would be an alkylating version. So if I had a bromine right there, I could alkylate at the alpha position. And so now I just have to work backwards now to make my cuprate. That's very simple. To make my aromatic compound, I think that's pretty simple too. This is something we could have made in the first week of the semester. And I can just alkylate benzene twice and then brominate on the benzylic position. I can get to my alkylating agent. Making the cuprate really just requires isopropyl lithium and copper chloride. Isopropyl lithium can come from isopropanol eventually, so that's pretty simple there. So then the question here is, how do I make this unsaturated compound that has, how many carbons do we have? 1, 2, 3, 4, 5. We've got 9 carbons here. So I could start with a 4-carbon piece and a 5-carbon piece if I needed to. However, we could observe that that's sort of aldol-like outcome. So I think there's probably many ways we could make this. We know how to install an alpha-beta unsaturated bond on an existing carbon chain. We also know how to make that bond using 2 smaller carbon chains. So we could do 2 different things here. So let's look at maybe both options if we can. If I used LDA to deprotonate that and I reacted that with this aldehyde, eventually if I dehydrated it, I could get that double bond to form. Of course, that aldehyde would come from the alcohol. That's not too complicated. And this carbonyl has 6 carbons in it. I'd have to add a carbon, and I can certainly do that by adding a Grignard to the 5-carbon aldehyde, and I can make both of those alcohol, both the aldehyde and the Grignard from an alcohol. So that's one way to do it. Another way, let's just use a different color here, would be to install alpha-beta unsaturation by alpha bromination. So if I had a bromine here and I used, say, a non-nucleophilic base, I could affect the elimination. And I can add bromine there via acid-catalyzed bromination, just with Br2 and H2SO, or H3O plus, I think is how our book shows it. So I could make that via the acid-catalyzed bromination. So, but how do I make this 9-carbon chain? Of course, this is relatively straightforward. We could make it from the Grignard, which would come from the aldehyde, which I have in blue next door, and the 4-carbon Grignard. And of course, we know how to make both of these from an alcohol too. So a couple options here. There's probably another option that I'm not remembering at this time, but maybe you can think about it. I bet you there's an option that uses more alpha carbon chemistry that will allow us to get to this desired intermediate too. So let's go ahead now and fill in the forward steps to make the alkyl benzene. We need, first step, T-butyl chloride, AlCl3. Second step, methyl chloride, AlCl3. To get to the benzyl bromide, we need NBS, radical halogenation of the benzylic position. To get to the lithium, we'd want to turn this into the bromine with Br3. Then we would want to use 2 lithiums. Remember, we need 2 lithiums because they each have 1 electron to share rather than 1 magnesium, which has 2 electrons to share. Then we could mix these with copper chloride, and that's what we get. 2 isopropyl lithiums plus copper chloride gives us the cuprate. We can, of course, oxidize the propanol with PCC. We can create the Grignard from methanol, PBr3, Mg. I can create the aldehyde via PCC oxidation of the alcohol. I can mix these two together, Second step, I'm going to use ammonium chloride again, NH4Cl, to work up. And then I think I need a third step here. It's going to be hard to squeeze it in. Forgive me here, but PCC to oxidize the secondary alcohol back to the ketone. And maybe I want to use bleach or Swern here if I'm feeling like I want to be a little more environmentally friendly. Now with the aldehyde, I can first mix the ketone with LDA. Then I can add the aldehyde, and I'm just going to put that right there. Then I might want to heat and add some base to eliminate. And so I can eliminate under acidic or basic conditions. Let's use acidic conditions here. So H2SO4 and heat will cause the beta alcohol to eliminate to the alpha beta unsaturated ketone, which I see up in blue here. Alternatively, I've already shown you how to make this compound, and we can make this from that alcohol. I'm not going to show you how to do that because we've done that already. We can mix these together. Second step, NH4Cl, work up. We know how to oxidize that. I'm going to use bleach in this case just for change up, NaOCl. And then I already showed the reagents I need right here. Mix those with the ketone to alpha brominate. And then I could use DBU here, if I wanted to remove an beta hydrogen to get the bromine to leave and create the ketone. And then, of course, I take my alpha beta unsaturated ketone, I mix it with isopropyl chloride first, and that would add the isopropyl group right here, leaving me with an anion in this position, or at least an enolate, which is nucleophilic here. And if I don't work that enolate up, I react it with an alkylating agent, I can put my alkyl group right here on the alpha position. So that's really all I have to do. I could draw a green arrow there if it makes you feel better, but I've already showed you how to do that final step. And so you can see there's a couple different ways to get to this desired intermediate. I bet we can think of more if we thought about it. Probably no other ways to get here or here, but oftentimes there's more than one way now to make a number of carbon-carbon bonds and come up with the functional groups that you need. Well, let's take a look at this third problem. We're going to use the same rules, of course. We can start with benzene and monoalcohols of 5 carbons or less. So if we look at this, we've got an alcohol at the top of our 6-membered ring, a couple of substituents on it. Of course, this alcohol could have come from a ketone. And if it comes from a ketone, I hope you see quickly that this problem becomes more alpha carbon chemistry. We now have an alpha position that has a methyl on it and a beta position that has both a methyl and a benzyl group on it. And so we could use the same theme we've used in the other videos here, and indeed I think that's the way to do this. You'll see where this problem branches off in a second or two. So I can certainly add the alpha methyl, and I can add one of those groups as a cuprate, but not the other one. So let's look at adding the benzyl cuprate. So we could have this cuprate, or if you wanted to just use one benzyl group, you could put the cyano in place there, and then you would not waste one of your benzyl groups. And of course we would need methyl. Let's use methyl iodide in this case because that's a liquid, a little easier to use than methyl bromide or methyl chloride, which are gases. And of course we need the alpha beta unsaturation here. So we know how to make these from alcohols. I might not even show that on this video. You saw that on the previous two problems. But now the question is, how do I make this compound? And of course this is an alpha beta unsaturated ketone, so this bond could have been made from a aldol reaction. And if that's the case, I would need this compound. I'm going to exaggerate a few of the bonds, but if I react that with sodium hydroxide and heat, I should produce this compound via loss of water. So I'm going to redraw this. Let's count our carbons here. 1, 2, 3, 4, 5, 6, 7. So these, of course, are the same. And so now you'll observe I have a 1,5-dicarbonyl compound. And we learned how to make those in the alpha carbon chapter via Michael additions, using enolates as a nucleophile to make this alpha-beta bond. And they would react with alpha-beta unsaturated carbonyl species, which would be this shape here. So we could do that. Let's take a look at that idea. So if I used acetone enolate and this alpha-beta unsaturated ketone, if I could turn one of these sides into a nucleophile, attack here, I could do a Michael attack and end up with my alpha-beta unsaturated carbonyl species. There's a couple ways to do this. We could do the stork enamine, which would be acetone plus a secondary amine, which could turn into an enamine, and that could be used as our nucleophile. Or, and let me use some red here, or I could do, instead of acetone as the nucleophile, I'd still use the same electrophile, but what if I used a 1,3-dicarbonyl species as my nucleophile? And if you remember, this is ethyl acetoacetate. This is nucleophilic at this position, could attack here. And later on, I can lose CO2, losing this group. And so that's an easier way to make that new CC bond as well. So we've got a couple options. So I could do this plus the alpha-beta unsaturated compound, or I could do the stork enamine. So let's look at how we would keep working backwards in this case. How do I make the alpha-beta unsaturated species? I could make that from butene-all if I wanted to. Or I could make that from formaldehyde reacting with acetone in an aldol reaction. Either one would be fine. This is probably easier because I have two functional groups here that I'd have to produce, whereas in this case I just have to come from methanol and isopropanol. So I think that's probably the easier way to go. But of course, this might be a challenge for you. How do you make 3-butene-2-all? That would be a good challenge to think about. Also, we could make ethyl acetoacetate via a claisen reaction of ethyl acetate. And I can get to ethyl acetate from ethanol plus acetic acid. And acetic acid comes from ethanol as well, so that can all come from ethanol. And then I just showed you how to make that compound, so I think we're done actually. Let's just make sure we all remember how to make cuprates. If I have benzyl lithium, I can use 2 of those plus copper chloride, and that'll make my cuprate. I can make benzyl lithium, of course, from benzyl bromide. I can make benzyl bromide from toluene, and I can make toluene from benzene. I can make methyl iodide from methanol, and I could probably use HI to create methyl iodide in that case. So let's work forward. I'm going to use purple to work forward today. So HI should turn methanol into methyl iodide, and I can alkylate with aluminum trichloride and methyl chloride, and then I can brominate with NBS, and then I can turn that into the lithium by adding 2 equivalents of lithium, and then I can mix that with copper chloride to make my cuprate reagent. I can make my acetone via PCC oxidation of isopropanol, and of course I want to point out again, we wouldn't make acetone if we were going to do this in real life. We'd buy it. In fact, we could probably buy this species. We could probably even buy this species instead of synthesizing it. But of course, this is more of an exercise to practice our synthetic techniques. It's a little more challenging and educational for us to have to start from simple alcohols. Going from methanol to formaldehyde, same process, PCC. Then I can mix both of those together in the presence of NaOH and heat. The acetone will get deprotonated. That's the only alpha carbon either one of these are the same alpha carbon, and it's more likely to react with the highly reactive formaldehyde than it is with another molecule of acetone. And so we'll get this butene-one, which we can react with another molecule of acetone in the stork-enamine synthesis. So if I wanted to react these together, I could mix, let's go from the other side. I could mix this with, I think, our textbook uses this 6-membered amine, and then you add the alpha-beta unsaturated compound. So that would be 2 here, and then 3 would be just acid workup. And you lose the enamine and protonate all anions that you need to. Alternatively, we could use Jones reagent, H2CrO2 or H2CrO4 plus plus water to get to the carboxylic acid. We can use some carboxylic acid chemistry and use ethanol plus H2SO4 in a Fischer esterification, and then I can use sodium ethoxide in a claisen reaction where we lose ethanol and make this beta keto ester. And then that beta keto ester can react with my unsaturated ketone in a Michael addition. And I think we would use the same base here, sodium ethoxide. And that would be the first step. Second step would be acid workup and heat. And that would actually drive off CO2, leaving us with our 7-carbon chain. Because you'll see here, we've got 1, 2, 3, 4 carbons, 5, 6, 7, 8 carbons, but we only want 7. So once we made a bond between here and here, this is free to leave as CO2 once we convert it back to the carboxylic acid, and that leaves us with this compound. And if I want to react that up to here, I just need NaOH and heat for an aldol, and we'll just write aldol there to remind ourselves that it is an aldol reaction. And now I'm at my alpha-beta unsaturated compound. I can mix that with the cuprate, as we saw in the previous videos. It attacks here. If I don't quench it, I'm left with an enolate here. The anion can react with methyl iodide to get me here. And then, of course, this is a pretty straightforward synthesis here, NaBH4 in methanol, to reduce that to the alcohol. And I would just like to point out, we could keep going here. We could do things with the aromatic ring. We could protect the alcohol or protect the ketone, add some things to the aromatic ring. It currently has a orthopara directing group on it, a mild activator. So we could do some more things here, or we could take this ketone or alcohol and do some more chemistry on that. So this doesn't have to be the end of the road. It's just the end of this particular synthetic problem. But you can keep going just for practice, or trade possible pathways with your friends for some additional practice.